All right, now we're going to continue the video on section 6.2. This part of it deals with just the variation part. Okay, there's really two types of variation. Two quantities can be related directly or inversely. Okay, so if we have a situation where if one quantity increases, the other also increases. So if one goes up, the other goes up. Or if one decreases, the other decreases. Okay, that type of variation is called direct variation. So if you have a job that pays $95 a day, your pay is going to increase if the number of days you work increases. That's what is called direct variation. Okay, and we say that the quantity y varies directly with x if there is some number that's not equal to 0, so some number, so that y would equal k, that number, times x. So this k right here, that's called the constant of proportionality. And in the case of the $95 a day example, the K was equal to $95 per day. Okay, so let's look at what we can do with something like that. So suppose we earn $95 a day. They want us to write a variation equation that describes the pay in terms of the days worked. Okay, so I'm going to let x equal the number of days worked, and I'm going to let y equal the pay. Then my equation that I could write would be that our pay would equal 95 times the number of days worked. So 95x means 95 times x. Right, now it says to use that, so that's the variation equation right there. Okay, now it says use that to determine your pay if you work 6 days. So if x equaled 6, then y would equal 95 times 6, and that would turn out to be $570. And if I wound up working 15 days, then y would equal 95 times 15. So I'd make $1,425. So as the number of days increased, notice that the pay went up as well. Okay, that's because this was a situation where the pay varied directly with the number of days worked. Okay. All right, now with question number 9, we actually had the k value. The 95 was actually the constant of proportionality. So we were able to write our variation equation. Sometimes we just have information for some specific case. Like with the $95 a day situation, we might not have known it was $95 a day, but we might have known how much money they earned for working 5 days, and we could have used that to come up with the constant of proportionality. Okay. That's the kind of thing that's going to be happening on question number 10. Okay. So here what I have are utility cables that are strung above the ground. So I'm thinking about it like telephone poles with a cable, that's running between them. It says the weight of a certain type of cable varies directly. So the weight varies directly with its length. So they didn't tell me a formula, but they kind of did by using that language. So if I let x be the length of the cable and y be the weight, okay, then I can write an equation that the weight varies directly with its length by writing that y equals k times x. So what it's asking us to do here is to determine what the constant of proportionality is. So find your K and then use it to figure out what the weight of a 75 feet of cable would be. So what we do is we take a particular instance, the 20 feet weighing 4 pounds, and we put those numbers in the appropriate spot. So Y is the weight, I'm going to put 4 there, and 20 is the length, so I'm going to put a 20 there. And so what I can do is solve for K by dividing by 20. Okay, so K turns out to be 1/5 if I simplify that, or 0.2 if I write it as a decimal. So now what I can do is write my variation equation by putting that 0.2 in place of K. Then I could use this equation for a variety of scenarios. What I'm being asked to do here is to find the weight, so find Y, if I have 75 feet of cable. So I'm just going to put a 75 right there and take 0.2 times that 75. Do that real quick. And I get 15, exactly 15. And that would be 15, oops, I almost wrote feet. It'd be 15 pounds. Okay. All right, so I did it that way because they asked me to, because they said, find K, so here's K, and then use that to write your variation equation, and then you can just plug the 75 in to the appropriate spot. But really, I could have used a proportion here. I could have said, well, 20 feet of cable goes with a weight of 4 pounds. So how many pounds would 75 feet be? I could have set up this proportion. I have to match my feet to feet, and then I would have my pounds in the appropriate spot. And this would be true because my variables are varying directly. So when you look at that, it's because your K would actually be Y over X. Your K would be this fraction, Y over X. And so like I know that's really K, and that's really K. So that's why it would be okay to do that. Okay, so I could just set up that proportion, and then I could cross multiply and take my 75 times 4, like so, and then come back in and divide by 20, and I would also come up with 15. And that would be pounds. Okay. Ooh, I wish I hadn't used X there, though. Let me change that, because in our original setup, I wish I had used Y, since Y actually represented the weight. So let me do that. Change all those to Y, so I don't have a different variable used there. If I really were doing the proportion approach without having done what we already did, what you call that variable wouldn't have really mattered. Okay. All right, so those are two approaches. The one on the left is the one that they're kind of guiding you to do, but I just wanted to mention the other in case you were wondering about that. Okay. All right, so let's look at another type of variation. All right, sometimes two quantities are related in this way. If one increases, the other decreases. And vice versa. If one decreases, then the other one increases. This is called indirect or inverse variation. So we could say a quantity Y is said to vary indirectly or inversely with X if there is a number that's not equal to 0, so that Y equals K over X. Remember, the direct one was Y equals K times X. This one, inverse, is Y equals K divided by X. And there's a common context that you might have some experience with where this is the case. So distance equals rate times time. All right, if I were looking at that, and I was going to think about the scenario in this problem. This problem says the time it takes to drive a certain distance varies inversely with the speed. Okay? What they're saying is that if I took this equation and got the t by itself by dividing both sides by r, then t would equal the distance divided by the rate. And we know that. We have experience trying to calculate how long it will take us to get somewhere. Well, that tells us that the time is varying inversely with the speed whenever that distance is a constant amount. So if a family has a cabin that's 378 miles from their residence, that 378 miles is like a fixed distance, then we could write a variation equation describing the driving time in terms of the speed, and it would be t equals 378 divided by r. Okay? And what they want us to do is to use that equation to figure out how long it would take us to get there if we were averaging 60 miles per hour. So we would just take that equation, and in place of the r, we could be putting the 60. So if r equaled 60, then we know t would equal 378 divided by 60. And that turns out to be exactly 6.3. And the units on that would be hours, okay? Since this was miles per hour and this was miles, right? So this is miles and this is miles per hour. We know time would then be in hours. Okay? All right, now let's think about this. Now they're going to average only 35 miles per hour. So when our rate decreases, okay, when the rate, the r, decreases, when r goes down, then wouldn't the length of time it takes you to get there go up, increase? Wouldn't it take you longer? So if you go slower, the time it takes you to get there is going to be greater. So on that one, that second scenario, we're letting r be only 35. Then our t is going to still have the 378 on top, but we're going to divide by 35. And when we do that, we wind up with 10.8 hours. And we have experience with this, so we know the faster we go, the less time it takes for us to get somewhere. Okay? All right, so in this case, the d being 378 was the k value, was the constant of proportionality. Okay. All right, now let's look at one more problem that involves inverse variation. All right, this one says the strength measured in pounds of a particular beam varies inversely with the square of its length. Okay, and then what they do is they give us a couple scenarios. So a 10-foot beam can support 500 pounds, and the question is, how many pounds can a 12-foot beam? So we don't know that. Can a 12-foot beam support? Okay. So what we're going to do is we're going to set up an equation using this information. The strength varies inversely with not just the length, but the square of its length. Okay? So I'm going to let x be the length of the beam, and I'm going to let y be the strength of the beam, and that'll be measured in pounds, where the length is measured in feet. Okay? And then I'm going to use that first sentence to write my formula, basically. I know the strength varies inversely, so it'll equal k over not just x, but the square of the length. So that would be over x squared. All right, then what I can do is find K. And I can do that by plugging in the known quantities that when the beam was 10 feet, then it could support 500 pounds. So K over 100 would equal 500. And if I solve for K by multiplying by 100, I get that K would equal 50,000. Okay. And then once I have K, then I'm able to take my equation here and replace the K, because that's now what I know the constant of proportionality would be, and plug it in. And so I could use that to answer a variety of scenarios. On this one, we want to know how many pounds a 12-foot beam would support. So I could take that 50,000 and divide it by 12 squared, and that should give me my answer. Okay, so 50,000 divided by 144. When I do that, I get approximately 347.2 pounds. Okay, so you see on this one, as the length of the beam, when the length went up, okay, the strength went down. The number of pounds it could support went down, varied inversely. So you got to watch problems like this. You might have thought you could just set up a quick little proportion, but watch. If I tried to do that, if I said that 10 feet to 500 equals 12 feet to x, then I'd come up with 10x equals 6,000 and x would equal 600. I would come up with the 12-foot beam supporting more weight. So you got to really be careful assuming that you can just set up any old type of equation or any old type of proportion. With inverse variation, what you could equate if you wanted to is look at how that equation, if I worked on what the K really was, the K is x squared times y. So I know if I have one situation, okay, one particular situation like the 10-foot beam being able to hold, 500 pounds, I'll put that in a minute, I could equate that with some other situation like a 12-foot beam supporting 347.2 pounds. Like, it's not actually a proportion that you could write. See, the constant would be equal to x squared times y. So I would know that 10 squared times 500 would have to equal 12 squared times something, okay? And then I could find that something by working this out. So I would get my 50,000 equals 144y, and then divide by 144. Okay? And when I do that, I'm back to the 347.2 about. Okay? All right, so I just wanted to comment on that because I think sometimes people think proportions can just be written in some simplistic way and it's going to answer the question. But you got to really watch it when things vary inversely. When they vary inversely, you can't just do that. You could do this if you understood it good enough. If you saw why, you could do this. This is kind of like if you've ever had Boyle's law, P1 V1 over T1 equals P2 V2 over T2. You know, there's laws and rules that are kind of written this way. But our approach will typically be to find K. So on all of these, find K, then use it to write the variation equation. Okay, and then go from there to solve the problem. All right, and then just remember that direct variation, your variation equation would look like this for direct variation, and it would look like this type of thing if it's inverse variation. And then watch the words of the problem, because like on that last one, we had the weight varying inversely with the square of the length. So we actually had to get a square on that denominator. Okay, I'm going to go ahead and stop the video here. You'll have some more practice with this when you get a chance to work through some homework on it.